Principles of Bioproduct Separation, Module 9, Elution Chromatography, Segment 4, Kinetic Analysis. With me, Yusuf from School of Life Sciences and Ethnology, Institut Teknologi Bandung. We have previously discussed about adsorbance, yield and purity, discrete stage analysis. In this segment, we'll discuss about kinetic analysis. The effect of dispersion for a solid phase flowing into a packed column is as shown in the figure. If there is plug flow without diffusion, reaction or dispersion, then this pulse would come out of the column unchanged. Pulses of all solids which entered at the same time would leave at the same time, determined by the flow rate and column geometry. It would leave unaffected by any chemistry. If solid reacts with the column packing, it can be retarded. The amount of retardation depends on the nature of this reaction. If the reaction involves slow adsorption and fast desorption, the retardation may be slight. If it includes fast adsorption but very slow desorption, the retardation will be major. Pulses of different solids will be retarded by different amounts, which is the basis of chromatographic separations. Dispersion is called biaxial mixing diverted by the packing because the flow may be laminar and because the bed may not be uniformly packed. Dispersion is a function of physical factors like velocity and column diameter, but not of chemical differences between solutes. Dispersion will spread both a pulse which reacts with the packing and a pulse which does not. Dispersion alone will not change the time at which the pulse exists. Reducing dispersion may more clearly separate concentration profiles and hence give a better separation. The actual diffusion and chemical reaction between solute and packing can be analyzed in terms of a 5-steps mechanism. First, the solute is transferred from the bulk solution to the surface of the packing. Second, it diffuses into the packing. Third, it reacts reversibly with the packing. This reaction may include adsorption, any surface reaction, and eventual desorption. Fourth, the desorbed solute diffuses back out of the packing to the packing surface. And fifth, it diffuses from the surface back into the bulk solution. In a bioseparation, the overall rate is typically controlled by diffusion into and out of the packing. This is because the diffusion coefficients of biological macromolecules, which are slow in any case, will be further hindered within the packing. Quantitative description of elution chromatography begins with the mass balance on the solutes as shown in equation 29. In many cases, the accumulation in the solution is smaller than that in the packing, and the dispersion is negligible. The simplified equation is shown in equation 30. The exact relation between Q and Y depends on the controlling step in the mechanisms outlined previously. If mass transfer between the bulk solution and the surface of the particles is controlling, then the concentration profile can be expressed by equation 31. If diffusion within the pores is rate controlling, the corresponding relation has the form as shown in equation 32. If first-order reversible chemical reaction is rate controlling, the concentration profile can be expressed by equation 33. Each special case will give a somewhat different concentration profile. The column length can be calculated using equation 34, whereas the concentration at the peak can be found by a mass balance and calculated by using equation 35. The concentration profile has a Gaussian form which can be calculated using equation 36 and equation 37. Both give the exact concentration of a chromatographic column as a function of the volume and a standard deviation. The standard deviation is a function of kinetic factors like the velocity and the mass transfer coefficient. For the next segment, we will discuss about scaling up chromatography. Until then, I am Yusuf from Institut Teknologi Bandung.